Find the vertical asymptotes of the graph of the following two functions. Our function on the left is a rational function, 5 over x squared plus x minus 2. Factor the denominator is x plus 2, x minus 1. Neither factor can be canceled by a factor from the numerator. Therefore, the zeros of both factors will give you vertical asymptote locations. X plus 2 is 0 when x equals negative 2. That's one of your vertical asymptotes. X minus 1 has a 0 when x is 1. That's another vertical asymptote. Remember, vertical asymptotes come from denominator factors that cannot be removed. The second function is natural log of x plus 4. Natural log is only defined when the part that follows it is positive. Can't be 0, can't be negative, not in the domain. X plus 4 is positive as long as x is greater than negative 4. The value at your cutoff for the domain is where your vertical asymptote will lie. Determine whether the graph has a vertical asymptote or a removable discontinuity, also known as a hole in the graph, at x equals negative 2. In this function, if you try to directly sub in negative 2, you get a 0 denominator, which is undefined. However, the numerator can be factored as a difference of two squares, x plus 2, x minus 2. Because you can remove the denominator by canceling, that leaves you with x minus 2. Because the factor in the denominator can be removed through canceling, that tells us that x equals negative 2 is a hole in the graph. In fact, if we were to graph this function, it would actually look like the line y equals x minus 2, but it would have a missing point where x is negative 2. Specifically, the hole would be at negative 2, negative 4 once you sub that in. Determine whether the graph has a vertical asymptote or a removable discontinuity at negative 2. For this function, we can factor the numerator. Negative 7 and positive 3 add up to negative 4 and times out to negative 21. So we can factor the numerator. However, there is no factor in the numerator that allows us to cancel out the denominator. And since we can't remove it, we have a vertical asymptote when x is negative 2, or at x equals negative 2. Find the one-sided limit if it exists. We have the limit as x approaches 4 from the right for the rational expression x over x minus 4. Now, this denominator is 0 when x equals 4, so we know that there's a vertical asymptote at x equals 4. Since we're asked to find the limit from the right side, over here upper right of your screen, when we approach 4 from the right, that means we can plug in values like 4.1, 4.01, 4.001. That's the value that you guys gave me in class. When we sub that in, you start getting a really large function value, and that tells me at that asymptote on the right side of it, the graph will increase infinitely. Find the limit as x approaches negative 5 from the left. I'm going to factor the denominator using a positive 5 and a negative 3. That lets us cancel the x plus 5s. 1 is all that's left in the numerator. X minus 3, that's the factor that survives after the canceling is over. This factor, x minus 3, gives you a vertical asymptote where x is equal to 3, and that's that red dashed line. The x plus 5 factor could be removed X plus 5 is 0 when x is negative 5. That's the x value at the whole. Substituting negative 5 into the surviving part of the fraction, we get negative 1/8. That's the y value at the whole, and consequently, because we have a missing point, and that's all, we don't have a vertical asymptote, as you approach negative 5 from either direction, you're approaching negative 1/8, and that's the value of your limit. Find the limit as x approaches 0 from the left. We have the limit of 4 plus 7 over x. If you want to split this up, you can. You absolutely don't have to. If you split, this first limit is just a constant of 4. The second limit, when we're approaching 0 from the left, you want to sub in a very small yet negative number because we're approaching 0 from the left. We're in the negatives, getting closer and closer to 0. Substitute that in, you get a really small number. Size is relevant, I guess, irrelevant. You get some really negative numbers is how I probably should say that, like in the negative thousands, because infinity will override a constant. When you're adding, that limit is negative infinity. And finally, we're going to find the limit as x approaches 0 from the right. Remember that our sine function, it oscillates up and down as we approach 0 from the right. Sine is defined everywhere. Sine of 0 is 0. 1 over x, that is not defined at 0, so let's investigate this limit. I've put the graph of 1 over x here on the right side of your screen. As we approach 0 from the right, we hit an asymptote, x equals 0 to be exact. The closer we get to the asymptote from the right, the larger our function values get. So that's an infinity. 0 plus infinity is infinity, and therefore that's the limit of this problem.